Okay, all right, yes. Yeah, hi everyone. I must apologize to you. I was supposed to be in in real time there. Unfortunately, something happened and I couldn't make it there. So we will deliver it through the Zoom. We want to generally talk about the evolution of the cellular technology and particularly on what is the uniqueness on what we see 5G. I wanted to say this is in general a discussion session. So if you have anything that is coming up, you may unmute the mic and speak. You can ask. I will finish in 30 minutes, so the time will be managed. But you can ask me whatever that comes up to you in time. You might have heard these words, Mr. Watson. Come here. I want to see you. This comes from somebody called the Alexander Graham Bell. He's the one who also started, as we see, as the American telephone and telegraph company, the AT&T. So he has been the inventor of of telephone. So if you look at the fundamentals of telephone network, probably a lot of you might not have seen an actual rotary telephone, but they looked like analog wires coming from what we call as a telephone exchange all the way to your home, probably 4, 5, 6 kilometers of length. And then that was the original way the telephones were operating. So these were what we call as these were devices that what we call as the phantom power devices. So the telephone itself didn't need any power because all the power came from the telephone exchange. So you had a differential pair of lines that were running on 48 volt, and then the analog signal will ride on that, and then some circuitry called the subscriber line interface circuit from the phone interface and the telephone exchange side will talk to each other and then provide us with the voice. At the telephone exchange side, we had multiple mechanisms. Originally, if you see the older pictures, we had physically people connecting these wires. We will originally talk to an operator at the exchange, and then they will connect the wires across to somebody else, and then we could talk. And then the automatic switching exchange came. So to start with, this idea of last connection point was called the last mile. In some cases, we also call it the local loop mechanism. So in all communication systems, these started as analog wires, and then slowly it evolved onto what we call, or we could see that the last mile could become wireless. So that is where we had the idea of wireless local loop, where remove the analog line and then put digital there. So that was the original form of wireless communication that started in the consumer domain. In these cases, these were fixed wireless phones at homes. You couldn't move to somewhere else, or you couldn't carry it along. Then came the car phones, which were also wireless local loop. You could carry it along, but within one city. And that is where probably the 1.5 generation of the mobile phones came. Okay, great. Yeah. So I'll continue. So if you can imagine, then we had the idea of, say, providing, say, wireless connectivity to an entire, a bigger geographical location. One idea was to have, say, you have a huge transmitter, and then you could have all this, what we call as the user equipment. But then we had the problem of what we call as the power. The big transmitter could transmit across to the smaller handheld, but the smaller handheld could not transmit to a station that was very far away. It could also problem of infrastructure. We could not have so many of these, say, devices connecting together to one station, and also had what we call as the highway problem. The spectrum that we are talking about, the road was not good enough. So what we did, we invented something called the cellular communication technique. Idea was to divide the geographical area to smaller cells and provide base stations. Now the problem of, say, power is reduced because now you don't have to transmit all the way through to the long distance. Secondly, we could have smaller roads coming together to become a bigger road, and then the bigger roads could have connected together. So we could use what we call as the frequency reuse idea. And we could also solve the infrastructure problem because the infrastructure got distributed. This is a fundamental idea of cellular communication idea, to say that we could divide areas into smaller segments so that the user equipment does not have to communicate very far. It could be within certain distance. So if you look at the first generation mobile systems, it was started in as analog, as we stated earlier. We had this NMT systems in Europe, the AM systems in the US. You could have seen this kind of big mobile phones from Motorola and guys like that. AT&T and Motorola were fighting to, who will build the first phones. And as you see here, we talked about the car phone at the very popular at the time. And this was using the analog FM modulation. So as you know, modulation, the idea is to say that rather than everybody speaking on the same frequency, we translate the frequency to another domain, and then you make the user speak only on that frequency. You can imagine you are in a, say, a reception room or a function room, and everybody's talking, then you won't be able to hear. But if everybody had a pipe that if you were to connect to somebody else, you connected through that pipe. That's the idea of modulation. And FM is a type of modulation that we can think of. Second generation was much more interesting. Now we had the idea of what we call as roaming. You could have a phone in a certain cell, but now because of the mechanism that we had, also look at these names. These names were also originated at the time. The basic initial connectivity station was called the base transceiver station. This was like the radio station. And then it got connected to something called a controller station, and there was a switching station. That was a generic idea. And we could see that this is already now, in this case, it has already become digital. The communication between the base station and the UE was already digital in this case. When we became 3G, the idea was that now, along with the voice information, you could also have the internet coming to you. So most of the mobile infrastructure remained the same, except that we have this, say, what we call as the gateways that will connect the internet service provider into the system, so that now mobile phones will be able to, say, generate or use some data as well. So that is where, if you remember, probably early 2000s, and by the time the iPhone came out, 3G mobile systems were very, very popular at that time. Then we have the fourth generation mobile communication system, which actually changed the way the phones work, because now the fundamental idea of the backend was already a packet network. If you remember, originally the analog systems, when it became digital, it was working under a system called the time division multiplexed system. One user is allocated one time slot, and then he continues to transmit in that time slot. Whereas here now, we accumulate packets, and then the transmission mechanism is similar to the Ethernet idea, where we have statistical multiplexing. Anybody can send at any time. There is no allocation for anyone. But because of the way it all worked quite well. And then we could integrate the traditional 2G and 3G systems back into the 4G domain. And that's the fourth generation mobile network system. As you see, the phones also evolved during that time. Then at that time, we also had this idea of what we call as the small cells, not very popular in Singapore. But the idea was, now we wanted to increase the coverage and capacity. If you think about it, for example, if you are at a home, most likely you are not moving from the home because you are already inside. So the base station that is outside can be used for people who are in the crowd or on the road or on the move. We could have a station that is inside home. So it looked like a Wi-Fi box that you can connect to your internet network. And then it automatically discovered the network. It automatically discovered the corresponding service provider and then connected back into the network. For example, if you are a Singtel, say, fiber service subscriber, you could buy this box. When you switch on the box, it will automatically find out that, okay, I am a mobile service station only serving one or two people in that home, and then connecting back into the network. this concept is there even in 5G, but in Singapore it is not very popular because our base stations, what we call as the macro base stations, are big enough to handle people inside and outside and wherever we are. So it doesn't matter much for us. But wherever there is one capacity problem where the outside macro base station cannot take enough people, enough subscribers, then they will offload the stationary subscribers into small cells. And when you have a coverage problem, you are in out somewhere, you have say broadband connectivity but not mobile connectivity, so you could have a small area within your home by having your own say station, and that's called the small cell idea. And the concept of HetNet means a collab or a combination of the two macro base stations and the small cells together, something like that. Now, if you look at the mobile standards, you have probably heard of 3GPP, which is actually the current main mobile standards organization. Previously, you would have heard something called GSM. This is Global System for Mobile Communication. And prior to that, we had the HC as well as the ECPTA, the European Conference of Postal and Telecommunication Administration. It was also called the CEPT standards, who originally started these standards. So if you think about it, the first generation standards were GSM. So the first 1G and 2G were GSM. Then when the 2G became 2.5 and 3G, then we had this UMTS standard. The long-term evolution is the 4G standard, and now we have the 5G standard. The standards keeps evolving in that direction. There is also an involvement from somebody called the ITU, the International Telecommunication Union. They will define the usage scenarios. Maybe in the next slide you could see here, if you see, the ITU defines the usage scenarios for what we call as the 5th generation. So or the standards defines in such a way that you could have say multiple objectives rather than having one single pipe that provides infinite bandwidth. Can we have, say, one, yes, have enhanced mobile broadband, but at the same time, can we have a network that can have very much low latency? It may not be as high throughput as we have with the mobile broadband, but it is ultra low latency. It is also possible to have, say, what we call as the IoT systems with the MMTC, massive machine type communication. So it divided 3 core areas and then defined some standards. Traditionally, the latency is in the 10 to 20 milliseconds range. Can we have, say, 1 millisecond range for 5G? Peak rates were around 1 Gbps. Can we get up to, say, 20 Gbps? Spectrum availability was in the range of 3 gigahertz. Can we go up to 30 gigahertz? So similarly, this concepts of, say, slicing the network idea was there. Slicing idea means using the same hardware, but with different capabilities, you are able to provide differentiated services for differentiated end users. For a normal user, we may not be able to see this because as a normal user of 5G, the only thing that we see is the increase in speed. Nothing else is visible to us. But in the background, we have the idea of Industry 4.0, the next generation industrial revolution that is trying to make the factory automation perfect. In order to make the factory automation perfect, you need 2 things. One, the low latency communications to read and then read the sensors and actuate the actuators. At the same time, you need to have infinite number of sensors connecting possibility in a small location. So these are all areas where the 5G said that I will be different from the traditional mechanism of one pipe, but now I can have differentiated pipes. This was possible, one, because of the way the service was instantiated. At the same time, the way the spectrum used and the way that the mechanism of connectivity was done, I'll go back in one step and say we use larger modulation order in order to achieve higher per hertz capability. So you could pack more bits into one particular spectrum. You can have a much, say, larger or bigger trucks. You have the same road, but you have, say, trucks that are much higher, so that you could carry much more load. Something like that you can imagine. So in order to do that, you have to have certain capabilities, but that's one way of doing it, by increasing the modulation. At the same time, you could aggregate. Previously in 4G, when the connection was happening, you could only connect, or one mobile uh, uh, device was only able to connect to one base station. You could do either, say, dual connectivity. Two base stations could connect to one mobile phone. We could also have something called carrier aggregation. You could have connected, say, multiple bands into, from the same base station, you could connect multiple bands into the same mobile phone. So these are possibilities that came up. There is also the concept of what we call as massive MIMO. The idea was that in 4G, most of the antennas were, we should say, directional or omnidirectional, in the sense that, you could have one antenna that is serving everyone. As we moved to 5G, we had the idea of massive MIMO, a small number of MIMOs, maybe from 4 by 4 MIMO to, say, 128 by 128 or 256 by 256 arrays of antennas, so that a group of antennas could serve one person. If you see this significantly enhanced the way the communications were made. And this massive MIMO concept also needed to have the idea of what we call as the beam forming. So you need to create a beam that focused onto a particular subscriber, rather than, as you see here, to generate a spectrum or a radiation pattern that fall into the entire set of groups. But here, with the way that the antenna array was made, you could focus them onto one particular person, and so on. If you look at the 4G, you could see this structure here. You can see, you can go outside into some buildings. You could see a base station building, and then you can have the antennas. The long beams that you see here are the antennas. And probably you could also see some of the, say, circular antennas that are here. These are probably antennas that carry the traffic back into the network. These ones, say, serve. Usually these will come in a 3-sector or a 6-sector way, so that a 120-degree coverage area of people will be covered by one antenna. This will cover another 120. There is another antenna on the other side that will cover the other side of the antenna. Sorry, are you able to see my screen? No. Just give me a minute. No, I am unable to do that. Are you able to see my? So this antenna is I'm talking about. These are the three 120-degree antennas, 1, 2, and 3. And these are the antennas on the backhaul system. So it looked like that. So we had only a handful of customers who were making all these systems. Nandu, everything okay? Okay, very good. Okay, all right, yeah. So if you see, this portion is what we see here. We have a mechanism of, these were very tightly connected systems. Only, say, 6 or 7 companies in the world could make this system. And the backend was, done by many other people. So when the 5G came, people decided that we need to break up the system, of having what we call as the baseband unit, and the radio unit needs to be split up. And then they came out with this idea of what we call as, say, a virtual RAN idea. Virtual RAN idea means you can have independent. This area was split. Okay, let me go back in 1 minute. Yeah, this area was split into the radio units and the digital distribution units. And the distribution units were equivalent of the base station, the baseband processing part, whereas the radio is the one that transmit out into the air. So you could, you defined very standardized protocols in between, so that now anybody can build a DU, anybody can build a radio, and anybody can build the backend. So it becomes a much more approachable ecosystem of innovation and more party involvement and so on. So 5G system inherently brings new players into the market. So you could see a lot more radio players in the market, a lot more base station players in the market. You could even take a normal computer, like an Intel-based server system, and you could download all the stacks, and then you can buy a standard radio and connect them, and you can start your own base station as such. See, you need to buy your license from the government. That's for another reason, but that's how things are evolving now. I will skip this slide. So look at some of the application examples. We talked about the enhanced mobile broadband, that is the EMBB. The idea is to have infinite number of, infinite amount of bandwidth. So this also help us to have, say, ideas like, virtual reality systems, or the 8K systems. We could have even, say, if you have, say, excellent bandwidth and low latency capability. This is an example where Docomo plays a real-time concert across the network. You could have a real-time view of the stadium, and then sit down in your say home and have the same view as if you were in the front seat in a stadium, by using one of this virtual headsets. And as you turn around, you could see exactly what one person could see from here. All these are the promise of 5G. I think it is not here yet, but these are the possibilities that we see with the enhanced mobile broadband. If you look at the URLLC, this is the ultra reliable low latency communication. You can have high reliability. That means you will fail once in a million times, and the low latency is like 1 milliseconds. So you could have the robotic surgery that we always talked about. The doctor moves his handle, and exactly the same way the knife would move. If you have latencies like that, then it becomes possible. It is possible. It's also possible with the remote equipment operation. If you have, say, very risky locations where we need to operate very heavy equipment, you don't need to be in the equipment. You can have a remote agent doing it through a control room, but you need extremely low latency and extremely high reliability possibilities. If you look at the IoT revolution, I think we talked about it earlier. This is the idea of having the factories becoming what we call as the dark factories. You don't need to switch on the lights because there's no human being working there. It's all automated. Everything is connected through the sensors, and that's possible because of the massive machine type communication possibility, EMTC. And you can have, the ability is to have at least 1 million connections per square kilometer. And that's what makes the smart cities possible. And that's the way the EMTC evolves. If you look at some of the performance targets of the application scenarios, if you see, say, the way that we feel, and if you need to have some tactile-like interaction, we are looking at a latency target of, say, 0.5 milliseconds. So you touch something, and at the same time, the other side of the network gets the feeling that you get the feeling that it is touched. At the same time, the other side also gets the touching. That's the way that the tactile interaction would work. And you could see other type of delay networks. We talked about the Industry 4.0 revolution. The idea was that from the simple automation techniques of the Industry 3.0, here it becomes smart connected. That's because of the IoT, AI, 5G capabilities that we have. And one of the key elements of enabling that is 5G, because of the defined connectivity that is possible, because of the low latency guarantee that cannot be offered by other wireless technologies. Wi-Fi or any other technology cannot offer the same type of guarantee and the same type of reliability on connection. We have the Industry 4.0 possible because of the capability. And that's one of the key of that is what we call as this time-sensitive network capability. Idea of time-sensitive network capability is if you have, say, like what we see earlier, we have a machine, we have a control room, and if you have a 5G network in between, the 5G will guarantee the time in to the time out, so that now we can operate certain equipment with certain definite possibilities. And that's where we are talking about the integration of 5G in Industry 4.0. Same as mobile edge computing. We have the factories. At the same time, they have massive connections, but we need to provide them with a huge amount of compute capabilities at the premises. And that's where the mobile edge computing comes into picture. If you see here, the connectivity comes into the base station, but the base station is equipped with what we call as the edge computing. This is probably not possible before, but if you see the latest news that we have, the data centers are offering 5G infrastructure. So the compute capability comes in. This is a traditional data center on a hierarchical form. And usually we have the layer of switches that is distributing the switching capability of, say, hundreds of thousands of computers. And now if we have these computers able to provide the capabilities we described earlier, these becomes the baseband units, and then you connect the radios, and then suddenly the data center has become a 5G infrastructure. And this kind of what we call as convergence of infrastructure is coming into the networks now. Moving on, there is another concept called private 5G. In private 5G, what happens is you get the spectrum for particular application. So, for example, NUS can get a particular spectrum from the government, and then the equipment that are used in the system can be particularly connected to that network. That's not Singtel, that's not M1, that's not StarHub, but an NUS network. And it becomes much more, say, dedicated network with enhanced security, with smooth integration and all capabilities together. And many of the service providers are offering this into the end customers. A number of large industries in Singapore are already using it. So I have rushed through the presentation to come to the 6G slide to say that moving from 5G to 6G, it is still in the early definition of what exactly is the meaning of 6G today. But as we said earlier, the ITUT has already come up with some usage scenarios. We call it the IMT 2030. The ITUT for the 5G was IMT 2020, where we had the description of, say, 1 millisecond latency, 1 million connections per square kilometer. All of this is now gone to one more scale, one more magnitude better. The target of 5G is to have latency of, say, 0.1 millisecond. The connection density becomes 10 million. The reliability becomes one-fold better. The mobility from, say, 250 kilometers or 500 kilometers per second kilometers per hour speed becomes 1,000 kilometers per hour speed. Therefore, every element that we are talking about is actually going the next generation. But it also provides the integration of, for example, it provides the immersive communication, the AI and communication, and the sensing and communication. These are the three areas that gets integrated into the network. For example, say if we were to have, say, the GPS, we know about GPS that provides the location in the outdoor today. But with the 6G, what we are expecting is that from the network, we could derive the location of the person inside a mall, in which floor he is. It's possible because if you have connectivity to 3 independent base stations, you can triangulate and find out exact location and so on. So such capability now comes integrated into the network itself. There is also, similar to the mobile edge computing that we talked about earlier, the number of AI capabilities that are existing as applications today will become part of the network, so that the application designers can make use of the capability of the network in order to perform various things. That's what is coming next when we get into the 6G capabilities. So we talked about the evolution that from the wired communication network in the last mile, we thought about removing that last mile wire and then having the wireless connectivity. The original connection was what we call as the wireless in local loop, no roaming, only within the house or to the cars. Then we saw 2G, 3G, and 4G. Coming to 5G, we had what we call as the differentiated services. We call the enhanced mobile broadband, the ultra reliable low latency communication, and the enhanced machine type communications. Then the applications of that were multiple. Industry 4.0 is a big one that is providing the dark factories. We also talked about the URLLC, the ultra reliable low latency communication that enables multiple capabilities, including precision automation. And 6G will drive, say, industry, the next generation of industry. But it becomes very interesting that now we need to see how the human and the machine will collaborate together. There is big discussion about the ethical practices that needs to be in place before we can get to the stage. And as we all know, we all talk about how we can incorporate sustainability and eco-friendly ideas into the next generation network designs so that we can have a smooth transition to the future network technologies. That's all from me. I am very, very sorry that I had to do this like this, but hope you had some insights, and welcome to have questions, please. Absolutely, I can. It can also be comments that you think or you know. It doesn't need to be that you need to know. You can also think that, oh, it could be like that. It could be like this. All ideas welcome. I couldn't hear you very well. Can you make it a bit more clear? Or you can type, I will immediately answer. Perfect. Now it is perfect. So, do you mean to talk about the way the actual physical modulation works, or the way that? No, I don't have that in this slide. It is a bit intriguing to think that, but maybe this is the closest that we can think about it. Um, so we have multiple mechanisms on how exactly the frequency management mechanism works. In the frequency division duplexing mechanism, every user is assigned one frequency for downlink and one frequency for uplink. In the time division duplexing mechanism, a user is assigned with one frequency. So it will transmit for some time, then it will stop. And at the same frequency, it will upload. And then the mechanism of this frequency, it's a bit involved, so that's why I didn't go in there. But the idea is what we call as the OFDM, the orthogonal frequency division multiplexing mechanism. This is quite interesting, but I mean, that would have taken one session by itself. That's why I didn't go through. But the idea was, in the same frequency, if you rotate the signals, then the same frequency can be used by multiple people. So you could transmit in the same band, but you can have multiple people talking because you are shifting the phase. So the mechanism of receiver will be able to exactly identify this shifting mechanism and be able to recover it and then use it accordingly. So before that is the idea of what we call as this quadrature amplitude modulation, which is actually, if you think about, if you have a series of bit and, bit series, if you can imagine what you do is you can switch on a frequency, you can switch it off, switch it on, switch it off, some mechanism can be arrived at in order to indicate zeros and ones. So here, what we do by the quadrature amplitude modulation, many of your engineering classes would have seen this. We will group these bits and then make them into a signal. I have a signal that is, say, for example, here, 45-degree sine, 45-degree cosine, and then with this amplitude. And if I can receive the signal, then I know that what the bits that are coming is 1, 0, 0, 0. If the amplitude, sorry, the angle is the same, but if the amplitude is higher and I'm getting a reception here, then I'm receiving 4 bits called 1011. So this is the quadrature amplitude modulation technique. This is how, with say lesser number of bandwidth, we can pack more bits. So you send only, so if you see here, you send only say 16 patterns here. But if you put all of them together, then you can have so many of them. So many of the bits are sent in one symbol information. So like that, you can pack multiple symbols. So these are multiple stages we can have. If there are much more enthusiastic friends, we can have. I kept it in the application layer, but there is much more details into it, and it's very intriguing, and it's quite easily explained in the YouTube videos if you want to see them as well. But if somebody speaks to you, that'll be much better.